Okay, let's look into potential energy and energy conservation in general. Let's review the definition of work, which was defined as U being the integral from R1 to R2 of sum of the forces dot dr. And we've also seen that U was also defined as the change of kinetic energy, which is 1/2 mv final, which I will call V2 squared, minus 1/2 mv initial, which I will write as V1. Now the idea is to assume and suppose that there exists a scalar function. Now, it's not a vector function, it's a scalar function, such that dv, which is our supposed scalar function, is minus what's inside this interval, so sum of the forces dot dr. So this is a vector dot another vector, so we know that has to be a scalar. So let's suppose that it exists such a scalar function, such as the derivative of the function is equal to minus the sum of the forces dot dr. So let's integrate both sides. We are going to integrate between V1 and V2. The left hand side, dv, equal minus integration between R1 and R2 of sum of the forces dot dr. Now since we know that the work is defined as the right hand side, let's move the sign on the other side. We end up with integration between V1 and V2 of dv is equal to the work, which is also equal to delta ke. Now we can integrate easily the left hand side. This becomes V2 minus V1 is equal to the work, which is also equal to delta ke. Now this can be written as delta V, so we can define the delta V as minus the work or minus the change of kinetic energy. Now this delta V is known as the change of potential energy, which is our scalar function. So let's remember for specific forces such as the weight, remember that the work was minus mg, which is w, y2 minus y1. So if the change of potential energy is minus the work, then it follows that the potential energy for the weight is plus w y2 minus 1y. Similarly from the spring, we know that the work done by the spring is minus 1/2 k s2 squared s2 squared minus s1 squared. Therefore the work done, or the potential energy due to the spring as is being stretched or compressed is plus 1/2 k s2 minus s1. Now if the spring starts at equilibrium, this is 0, and therefore it's just 1/2 k squared. So really the potential energy is very similar to the work. Obviously they have the same units, and the only difference between work and potential energy is just a sign difference. So let's see how we can expand this idea. We are going to use this relationship. So we're going to bypass the work and relate the change of kinetic energy with the change of potential. So we have V2 minus V1, which is delta V, is equal to minus kinetic energy at instant 2 minus kinetic energy at instant 1. Now I'm missing my minus sign, so this becomes positive and this becomes negative. Now if we want to generalize this relationship in a situation where there are several potential present, then we can expand this to the sum of all the potential present is equal to the change of kinetic energy of the system. Now we could be dealing with a system that has a spring present, gravity present, so the weight is going to have a change of potential energy, the spring is going to have a change of potential energy, and then we can add friction, which is considered a non-conservative force. So we can consider all the potential due to all those forces. And all we have to do is stick a man in the left hand side. So let's imagine we have the case of all those spring, gravitational forces, and non-conservative forces present in our system. We can rewrite the left hand side as the V final due to the spring minus V initial due to the spring. Then if we have to consider the force due to gravity, we can add the potential difference due to gravity. So V2 due to the weight minus V1 due to the weight. Then let's include whatever non-conservative forces that might be present. Let's write it as change of V of non-conservative forces. This must be equal to the change of kinetic energy. And this is known as conservation of energy. Which is nothing else than just look at all the forces present in your system. Calculate the change of potential energy for each force, add them up, and then set this equal to the change of kinetic energy. So again, let's refresh ourselves that if you deal with a spring, those two will be 1/2 k s2 minus s1 squared. If you're dealing with a gravitational field, then V2 and V1 due to the weight will be just W y2 minus y1. Kinetic energy is defined on 1/2 mv squared. And then the change of potential energy due to non-conservative forces in the case of friction will just be US, the normal force, which is W. Now if you're dealing with a system that has no non-conservative forces, which means that you only deal with forces that are conservative, then this term just drops out. And then you can move all this on this side, and therefore you end up with just change of potential energy plus change of kinetic energy. This will be V2 minus V1 of the spring, of the weight. This will be back to KE2 minus KE1, because remember here was the opposite of it. And this must be equal to 0. So this is the same thing as this conservation energy law, except only for conservative forces. So if you are not sure if you have to deal with the non-conservative forces, just add up all the potential energy difference, add to it the kinetic energy difference, and if it's equal to 0, you know that all your forces are conservative. If you end up with a non-zero value, then E must be minus delta V of those non-conservative forces. So if it's not equal to 0, you know you have to deal with non-conservative forces. So in practice, when you use this law, all you have to do again is start with this, do a free body diagram, look at all the forces present, allocate every individual force. If you have a spring, then you're going to have change of potential due to the spring. If you have a weight, and you have to consider the weight, you have to write down the change of potential energy due to the weight, and you equate this to the change of kinetic energy. And if you have non-conservative forces present, you just add one more term. And that's it.